All right, so let's dig into this age-old question. Can we actually predict earthquakes?
Hmm.
You've sent over some really interesting sources for this deep dive.
Yeah.
We've got articles from scientific journals, info right from the USGS website, and even a blog post from a solar physicist.
Wow.
Seems like it's going to be a fascinating conversation.
Yeah, it looks like we've got a real clash of viewpoints here. On one hand, we've got the USGS, pretty much the authority on this,
Uh,
saying, nope, earthquake prediction just isn't possible. But then on the other hand, you've got this new study using AI that's showing some really promising results.
Right.
It's this kind of contrast that makes these topics so interesting to explore.
yeah, absolutely.
Yeah.
So let's unpack the USGS stance first. They're pretty straightforward. They say no earthquake prediction.
Mm-hmm.
What's the reasoning behind that?
Well, their stance really boils down to their definition of prediction.
Okay.
To the USGS, a true prediction needs to have the date and time, the location, and the magnitude of the earthquake.
Yeah.
You need all three of those things for a prediction to actually be useful for preparedness and mitigation.
Right. That makes sense. It's not enough to just say an earthquake's going to happen someday, somewhere. We
Exactly.
need the specifics to actually take action. But what about all those past claims of earthquake prediction?
Right. Well, the USGS points out that many of these past claims, they lacked scientific evidence. They were super vague, or they were just predicting the inevitable, like saying there's going to be an earthquake someday.
Right.
For a prediction to be credible, it needs to have solid scientific backing.
So the USGS sets a high bar for what is a true prediction. But then we have this research coming out at the University of Texas that uses AI to predict earthquakes with 70% accuracy a week in advance.
Yeah.
This was in a region of China that's got to have the earthquake science community buzzing right.
Oh, absolutely. 70% accuracy, that's a huge leap forward. Previous attempts at prediction haven't even come close to that level of success. What's really cool about this study is that they use AI technology and a massive amount of data from this system called AET.
Okay, so break down this AETA system for me.
Sure.
Sounds pretty sci-fi.
It is pretty impressive. Picture this. 150 stations across a region in China, each one equipped with all these acoustic and electromagnetic sensors that are constantly listening for tiny vibrations and disturbances in the Earth's crust.
Wow.
It's like having a network of high-tech ears to the ground.
So constantly gathering data on any ground movement that could signal an earthquake.
Exactly.
But how do they actually use AI to make sense of all of that information?
Well, that's where it gets really clever. They used a technique called principal component analysis, which essentially simplifies huge amounts of data by figuring out the most important patterns and trends. Imagine you're trying to find a needle in a haystack.
Okay.
But instead of searching through every piece of hay, you have a tool that highlights the places where the needle is most likely to be.
Right. Okay. That's a good analogy.
Mhm.
So they use this principal component analysis to streamline all of that data from the AETA system.
Yeah.
And then they fed that simplified data to their AI model.
Exactly. And the AI was able to learn from years and years of earthquake data and find those subtle patterns that usually come before an earthquake. Think of it as training the AI to recognize the warning signs.
That's amazing.
Yeah.
But while 70% accuracy is really promising, I imagine there are limitations. Can this AI system be applied to other earthquake-prone regions around the world?
Yeah, that is the big question. The researchers themselves, they admit that their AI model needs to be tested and maybe even tweaked using data from other earthquake zones, places like California or Japan. Each region has its own unique geology and earthquake patterns.
Right. It's like trying to predict the weather. A forecasting model that works perfectly in Florida might not be accurate in Alaska.
Right.
So the next step is to see if this AI system can be adapted globally.
Yeah.
But there's another hurdle, right?
Mm.
Funding.
Yeah. Unfortunately, this kind of groundbreaking research is often really hard to get funded. It's a bit of a gamble for investors.
Yeah.
And honestly, a lot of this work is done by passionate scientists in their free time because they just want to understand these incredible natural events.
It makes you wonder what could be achieved with more resources dedicated to this kind of research.
Mm.
Okay, so we've tackled the USGS viewpoint and explored the advancements with AI.
Mm-hmm.
But now let's get into some more out there ideas. We have sources that suggest a possible link between solar flares and earthquakes.
Okay.
This is where things start to get interesting, right?
Definitely a big jump from AI and sensors to the idea that the sun's activity might be influencing things here on Earth. But that's what makes this deep dive so fun. We're looking at the edges of what we know and stepping into the unknown. It definitely is a leap from that world of AI and sensors and things that we can measure into something that's Well, a little more ethereal, could the sun's activity actually affect things here on Earth?
Yeah, and that's what's so cool about these deep dives.
Mm.
Sometimes we're looking at things that are pretty concrete, and then other times it gets a little more
Yeah.
whoa, whoa, whoa.
Boom.
So let's dig into this solar flare connection. So we had these powerful bursts of energy from the sun, right? And specifically these charged particles called protons that are just bombarding the Earth.
Uh-huh.
And the theory is that they somehow interact with quartz crystals in the Earth's crust.
Right.
But how does that actually trigger an earthquake? I mean, it sounds pretty wild.
It's a pretty bold theory, but the science behind it is actually quite interesting. So quartz crystals have this weird property called the piezoelectric effect.
Okay.
And what that means is when you squeeze or compress a quartz crystal, it actually generates a little electrical pulse.
Okay, so squeezing a quartz crystal makes a little bit of electricity. But how does that tie into solar flares and earthquakes?
Well, the theory is that when those solar protons, which are traveling super fast when they hit the Earth's magnetic field, they create these strong electromagnetic currents. And these currents can go deep down into the Earth's crust. And if they run into quartz crystals in fault zones, they could create those electrical pulses, which could basically give the fault like a little jolt.
So it's like the Earth's getting zapped by these solar protons, and then those little electrical pulses from the quartz crystals could be enough to set off an earthquake on a fault that's already under stress. I'm trying to picture it's like the Earth's getting a static shock from the sun,
Right.
and that little zap is enough to trigger a massive earthquake.
That's a really good way to think about it. It's definitely a cool idea. But of course, with any big scientific theory, there are people who aren't so sure. Remember that study from 2013 that looked at 100 years of data on sunspots and geomagnetic activity?
Yeah.
They didn't find a direct connection to earthquakes.
Right, but this new research is really focusing on the effects of solar protons, not just general solar activity. Could that be the difference?
Yeah, it could be. That's definitely something to think about. And it's worth noting that there have been other studies that have found connections between geomagnetic storms, which are often caused by solar flares,
Right.
and earthquakes, especially in areas with a lot of quartz in the crust.
So it sounds like we need more research to really prove or disprove this connection. It's like we have a piece missing from a puzzle. We've got some clues, but we're not sure how they all fit together yet.
Yeah, exactly. And that's what's so great about science. It's an ongoing process of exploring and discovering. Now, since we're talking about things outside of Earth that might affect earthquakes, let's go back to those earth tides we talked about earlier. Remember, we're talking about the moon and the sun's gravity pulling on the Earth?
Right, the same forces that create the ocean tides.
Right.
But instead of the water moving, it's the actual ground that's rising and falling just a little bit. It's kind of mind-blowing to think that something happening millions of miles away can affect the Earth's crust.
It really is. It's a great example of how interconnected everything in the universe is. And while these earth tides don't cause earthquakes directly, some scientists think they might play a role in triggering earthquakes on faults that are already on the verge of slipping.
So it's kind of like that straw that breaks the camel's back.
Yeah, like that. Like, imagine a fault line that's already under a ton of pressure from the tectonic plates pushing against each other, and then a high tide comes along, caused by the sun and moon lining up.
Right.
And it adds just a tiny bit more stress. Could that little bit be enough to set off an earthquake?
That's the idea. The problem is we have no way of knowing which faults are at that breaking point.
Yeah.
So even if there's a link between earth tides and earthquakes, it doesn't really help us predict exactly when and where an earthquake's going to happen.
It's like knowing a balloon's going to pop if you keep blowing air into it, but not knowing exactly when. It could be the next breath, or it could be 100 breaths later.
Perfect analogy. It really shows how complex this all is. We've got these external forces like the pull of the sun and the moon that could affect things, but we're still missing that one key piece to make accurate predictions. It's fascinating, but also a bit frustrating. We're learning more about what causes earthquakes, but we haven't figured out how to predict them yet. But wait. We can't forget about the wildest connection we've talked about, the one between cosmic rays and earthquakes.
Oh, yeah.
This is where things get really cosmic, right?
Definitely. The CIRIDO project, which looked at data from all over the world, they found this statistically significant link between how many cosmic rays are hitting the Earth and how strong earthquakes are. But here's the really weird part. There's a 15-day delay between when the cosmic rays increase and when earthquake activity goes up.
Yeah.
A 15-day delay. So it's not like we can say, hey, cosmic rays are spiking, watch out for an earthquake tomorrow. It's more like cosmic rays spiked 2 weeks ago, so maybe we'll see more earthquakes soon. But how could something happening in space so far away affect things here on Earth with that kind of delay?
That is the question that has scientists scratching their heads. And it gets
Well,
even weirder. This connection between cosmic rays and earthquakes, it follows a cycle that's kind of like the sun's activity cycle.
which is about 11 years long, but get this. The peak in earthquakes doesn't happen at the same time as the peak in solar activity.
Wait, so the cosmic ray cycle is like the solar cycle, but they're not synced up? That doesn't make any sense. It's like two clocks running at the same speed, but showing different times. What could explain that?
That's where people start talking about dark matter. Dark matter is this mysterious stuff that makes up a big chunk of the universe's mass.
Right, dark matter. We can't see it, but we know it's there because of its gravity.
Exactly. And some scientists are saying maybe, just maybe, dark matter interacts with both the sun and the Earth in ways we don't fully understand yet.
So we've gone from AI analyzing tremors, to the sun zapping the Earth, to the possibility of dark matter playing a role in earthquakes.
Right.
It's like we started with a deep dive into the Earth's crust and ended up in a cosmic mystery.
And that's what's so cool about this field. It's always pushing the boundaries of what we think is possible, showing us new connections, and challenging how we understand the forces that shape our world.
So we've gone from the depths of our planet to the far reaches of space in this deep dive.
We have.
And it seems the more we learn about earthquakes, the more we realize how much we don't know.
It's true.
But let's maybe take a step back for a second and talk about what we can do. Even if we can't predict earthquakes perfectly, are there things we can do to be better prepared?
That's a really important question. And the good news is, even though we can't say exactly when and where an earthquake is going to hit, we've come a long way in understanding how to reduce the damage they cause.
So it's more about being proactive and mitigating the potential damage than waiting for a prediction that might never come.
Exactly. And one of the areas where we've made the biggest difference is building codes in earthquake-prone areas.
Yeah.
They've changed dramatically over the years, incorporating what we've learned from past earthquakes and advances in engineering.
So buildings made with these modern codes are more likely to survive an earthquake.
Yeah, they're designed to be tougher, more flexible, and better at absorbing the energy from seismic waves. Think of it like designing a building to kind of move with the earthquake instead of trying to stay rigid.
That's so cool. It's like teaching a building to dance with the earthquake instead of trying to fight it.
Exactly.
What about early warning systems?
Oh, yeah, those are amazing.
I've heard of those, but how do they work? And how much warning can they actually give people?
Well, they use these networks of sensors that are placed all over earthquake zones to detect the very first waves of an earthquake. The P waves, which travel really fast and arrive before the more damaging S waves.
So it's all about catching those first tremors and sending out alerts before the serious shaking starts.
Exactly. And even though the amount of warning time depends on things like how far away you are from the epicenter, even a few seconds can be really valuable.
Yeah, I bet even a few seconds could give people enough time to get under a desk or move away from windows. Or maybe even trigger automatic safety measures in important things like power plants or transportation systems.
Absolutely. Those few seconds can make all the difference. And even beyond those immediate actions, early warning systems can also automatically shut off gas lines to prevent fires and slow down trains to avoid derailments.
Wow, it's amazing how technology can buy us those crucial seconds. But what about strategies for the longer term? I've heard about earthquake forecasting. How is that different from prediction?
Great question. So prediction tries to be super precise, while forecasting focuses on probabilities over longer periods. So instead of saying, there will be a magnitude 7 earthquake in San Francisco next Tuesday,
Right.
forecasting might say, there's a 50% chance of a magnitude 6 or bigger earthquake happening in this region over the next 30 years.
So it's more about understanding how likely earthquakes are within a certain time frame and area rather than trying to pinpoint specific events.
Exactly. And while it might not seem as exciting as a pinpoint prediction, earthquake forecasting is incredibly useful for long-term planning. It helps us make decisions about where and how we build, what kind of infrastructure we need, and how we educate people about earthquake safety.
It sounds like a great way to make our communities more resilient, even with all the uncertainty. It's about shifting from reacting to earthquakes to proactively preparing for them.
Exactly. And speaking of proactive measures, one of the most important things is public awareness and education. The more people know about earthquake hazards, the better prepared they'll be to stay safe when an earthquake hits.
You know what they say, knowledge is power. And in this case, knowledge about earthquakes can actually save lives.
I totally agree. It's all about giving people the tools and information they need to take charge of their own safety and preparedness.
This has been an amazing deep dive.
It has.
We've talked about AI, the sun's activity, Earth tides, and even dark matter. And while we might not have all the answers about predicting earthquakes, it's clear that we're making real progress in understanding them and reducing their impact.
Yeah.
What do you think is the most promising path forward for us?
That's a tough one because all of these areas of research add something valuable to the picture. I think the key is to work together and combine all of these approaches. Imagine using AI real-time monitoring systems and a deeper understanding of how the Earth and even the cosmos work all together.
It's like weaving together different threads of knowledge to create something stronger and more resilient. And maybe someday that tapestry will help us finally unlock the secrets of earthquake prediction.
Maybe someday.
But until then, the exploration continues.
Definitely. That's what makes science so exciting. It's a never-ending journey driven by our curiosity and our desire to understand the world around us.
Well, this deep dive has certainly sparked my curiosity, and I hope it's done the same for you. What was the most interesting part for you? Was it AI, the cosmic connections, or maybe something else entirely? Whatever it is, keep exploring, keep asking questions, and keep that curiosity alive. Until next time, happy exploring.